Define reasonable.
This is all reason.
Matter waves?
Oh, this is gonna get weird.
Oh.
Not reasonable at all. Okay, well,
I'm just, you asked, I told.
I asked, yeah.
If you don't, this is the old adage, if you don't wanna know the answer, don't ask the
Well, I'm gonna
question.
know the answer really hard here in a minute. I'm sure I'll have a great time with it tonight.
I'm sure you will. Okay, so
Take it out. We're learning something stupid.
here's the basic idea again of the photoelectric effect, and this is gonna play into what we're gonna do next. So, this whole idea that came out of this, if nothing else, it was the idea that it was this debate about whether light is a wave or is light a particle. And this is literally why it's called wave-particle duality. So it's a photon that travels like a wave, which sounds really, really weird because basically you spread this function out, but then once it interacts with the electron, then you get that interaction where then it acts as like this small little marble that hits the electron and gives it like a paintball burst of energy, and it goes, oh, I'm free, and the electron goes flying off, which you can't see because it's so small. But then we go, well, how can we detect it? And it was like, oh, okay, we'll set up a voltage, and that will allow us. So that will, okay, you're spotting the draft just dropped. So, yeah, you were up there, now it's just like, whoa, okay. So, again, physically understand what they could control, okay? So, and this is the whole idea when you're trying to find the identity of the unknown metal. You shined a bright enough light on there so that you made the photoelectric effect happen. Then you adjusted the voltage to stop it. And that goes to that equation that your K max, which is the same thing as your stopping potential, okay, is the difference between the energy of the photon and the work function, okay? That's the difference. So we can't measure that directly. We can't watch an electron going across and go, oh, here it comes. We'll measure the initial velocity and we'll measure the gap and we'll know how long it takes. And oh, here's this one electron that comes across the screen and bam, got it. This isn't like second grade outdoor activity on the last day of school where you have races going across. And maybe you bet on the individual. Okay, I got the electron in lane 5. Okay, I think that one's going to make it across first. Okay, as a matter of fact, it gets weird, Connor. But since all the electrons that we've ever studied have been identical, like no variance whatsoever. That one idea is that all electrons, just one massive electron, it's just all one big wave function. And that's why all electrons are the same, and that gets even weirder. So, here's the point of these graphs, okay? So like on that graph on number 29, okay? So, you've got frequency. Well, by an indirect measure of frequency, what are you measuring? Energy. Of what? The electron or the photon? Photon, okay? And then over here, then you've got over here you've got your energy values. So the whole point being is that there's a flat line. So, but then all of a sudden it takes off. So there's a couple of things that are important about this. Number one, in the classical world, where energy states can exist in a continuum, there should not be a flat line, okay? That should be indicate like no matter what, if you give it enough time, those electrons are going to gain enough energy levels because they can exist in a continuum. By virtue of the fact that there is a unique starting point that says that these electrons absorb a certain quantum of energy. There's a threshold that has to be met. And once that threshold is met, then it becomes a linear function because of the fact that frequency is directly proportional to the energy of the photons. So on 29, you should have two lines, one for sodium, one for calcium. If you want me to think they're parallel, you draw them parallel. If you want me to think that they are different sloping lines, draw them that way. When you get to 37, it's the same idea, okay? So what do those lines look like? Make sure that you have labeled them, calcium and sodium, so I know which one is which when you draw 37. Okay, any questions on the lab? Going once, and twice, sold. So at some point, get that handed in. It's what it could be. I made it.
They broke that one, didn't he?
I know, I haven't fixed it.
It's all Jaden's fault.
I was thinking, I said it to something now. Okay.
Because it needs to stop. You need negative voltage, so it stops.
But it requires the photons to be at a certain energy to even be released.
Yeah,
Which is
so if you do that low enough,
but then, what would happen
Now, anytime anybody makes a mistake.
It's a bad state for a compound. The inspectors come into the interviews.
you need a negative voltage to stop. That's how it is.
That sounds really weird now that I say it.
Yeah. I feel like
I was the governor's scholar.
It was boring.
Sean, why do you
I looked really tough at the end of
me off? Because like,
I was like, if I don't look now,
I'm studying how to do anything.
here's the thing with me, and you and Charles are both guilty of
And then it
that.
was
He
like,
made a
okay,
comment about
okay.
minus information every day. You don't wear your lanyard. I haven't worn it all.
Yeah,
Minus
that was the last today.
minus 1.
They stopped caring, so I stopped caring.
So I stopped caring.
I took second because she screwed me
Pretty
over.
sure I got off my
Because
back
she
about it. I have
qualified for
very
something, but we were within second.
Literally, as soon as my teacher stopped
I
caring,
can even tap the bottom of
I
the.
still have it though.
I skipped over it the first time and wrote
Boston
the rest.
was going down.
Guarantee you, Charles is about to call me a nerd. But
Yeah.
yeah, like,
It's tough.
thank you, Charles. I have a time turner hanging in my rearview mirror.
Danny, we're still going?
yes, that right.
All right, so one of the kind of famous things that came out of quantum mechanics is what's known as the Heisenberg uncertainty principle. So usually just call it HUP. And so this is, it isn't law, but it's pretty close. It's like a principle. So mathematically, what this says is that when you go to measure something, you can know one of two quantities. You can either know the exact value of the rotational or uncertainty momentum. This is what we talked about kicking the soccer ball, okay? So if you know that the soccer ball is within a certain range of possibilities of velocities, okay? So we know the soccer ball could be moving at a certain distance around the field with a certain amount of velocity, okay? So we would know a pretty good idea of that in terms of its motion. But imagine that the soccer ball is like smeared out over a range of possibilities on the soccer field, okay? Now, unfortunately, by the act of finding it, Jaden's going to kick it, okay? Now you've collapsed the wave function. By the fact that you found it, by kicking it, that's like hitting it with a photon, then you've lost track of what the possibility of the velocity could be. So if you know where it is, then by the act of finding it, then you've lost the other side of this. So this is why these two values are multiplied together, because they reach the same value of h, which is Planck's constant, over 4 pi. So typically, technically, it's greater than or equal to. Everybody just treats it as an equal sign. So these two numbers multiplied together always have to equal the same constant. So mathematically, what that means as one goes up, the other one goes down. Now, this is uncertainty in momentum. What two things do you multiply together to get momentum? Mass and velocity. So you either have an uncertainty in mass multiplied by a velocity, or you have a certain quantity of mass and an unknown velocity. So uncertainty has to come into play one of those two situations. It's either in mass or in the velocity. So I'm going to read you excerpts from this book, right? Alice in Quantum Land, which comes from the book Alice in
Wonderland.
Wonderland, okay? Anybody know the role, what the term the Mad Hatter came from? Yeah?
Hatters, they used to soak hats in mercury, and the fumes from the mercury would actually make them go crazy because it would eat away their brain.
Exactly. So if you were saying you were crazier than a Mad Hatter, then that's stock and trade went up. We need to have like a draft board. You know, like, okay. You're not even in the class. You're just, yeah. Trade went up on that. And so you would say, oh, you're crazier than a Mad Hatter. That was one of the reasons they stopped using mercury, even though mercury's really cool. Like my physics teacher at high school, he had literally, there was like a glass jar, and he had liquid mercury in it. And like if we got done with the test, he would like pour it out on the table, and we would like bat it around like a hockey puck on the table. That was like our prize for being good students. So we got to play with liquid mercury. I'm okay. So, it didn't affect me that much. It did end up becoming a physics teacher. Anyway, so just kind of sit back. It's story time. Okay? So obviously the main person in the story is Alice. So Alice was bored. All her friends were on holiday or visiting relations, and it was raining, so that she was marooned indoors watching television. That's kind of a boring part. So she stared.
We're going to have a story time?
Yeah,
Yes.
we have Alice in Quantum Land.
Oh, do you want a snack or a drink? Or
What do you got?
yes.
Oh, man.
Leave these poor lads and lassies alone.
I don't know.
No guarantees we'll burn down the room.
Teach it, Kevin, teach it.
All right, people. So
Finish the story.
time for the TA to teach.
I just said they keep going. I can read. It may be shocking, Connor, but I can read, so I've got to grab the word.
Our guy's already there. Whoa. Lacrosse.
They had a snack break. Like steak, hamburgers, lobster? No, cookies. All right.
Good enough.
Bacon. Okay. So,
And they came around with those.
so she's watching television. Back to the story. She stared in frustration at the screen, which at that moment carried a picture of the Prime Minister telling her how, all things considered, everything was really far better than it had been 3 years ago, even if it didn't always seem that way. As she watched, she was mildly surprised to see the picture of the Prime Minister's face slowly break apart into a mist of bright dancing speckles, which all seemed to be rushing inward, as if they were beckoning to her. "Why," said Alice, "I do believe they want me to follow them in." She leapt to her feet and started towards the television, but tripped on the book which she had discarded so untidily on the floor and fell headlong. As she fell towards, she was amazed to see the screen grow enormously, and she found herself in among the swirling speckles, rushing with them down into the picture. "I cannot see anything with these dots swirling around me," thought Alice. "It's just like being lost in a snowstorm. Why, I cannot even see my feet. I wish I could see just a little. I could be anywhere. At that moment, Alice felt her feet strike something solid, and she found herself standing on a hard, flat surface. All around her, the swirling dots were fading away, and she found that she was surrounded by a number of vague shapes. She looked more closely at the one nearest to her and observed a small figure, roughly coming up to her waist. It was exceedingly difficult to make out, as all the time it kept hopping rapidly to and fro, moving so fast that it was very difficult to see it all clearly. The figure seemed to be carrying some sort of stick or possibly a rolled umbrella, which was pointing straight up in the air. "Hello," Alice introduced herself lightly. "I am Alice. May I ask who you are?" "I am an electron," said the figure. "I am a spin-up electron. You can readily tell me apart from my friend over there, who is a spin-down electron." So, of course, she is quite different. Under his breath, he added something sounded vaguely rather like "Vive la différence." As far as Alice could see, the electron looked very much all the same, except that her umbrella, or whatever it was pointing down toward the ground. It was very difficult to tell for sure, as this figure also was jiggling to and fro as rapidly as the first one. "Oh, please," said Alice to her first acquaintance, "would you be good enough to stand still for a moment, as I really cannot see you at all clearly?" "I am good enough," said the electron. That's a Cohen line. "I am good enough. But I'm afraid there is not room enough. However, I will try." So saying, he slowed his rate of jiggling down. But as he moved more slowly, he began to expand sideways and become more and more diffuse. Now, although he was no longer moving at all quickly, he looked so fuzzy and quite out of focus that Alice could no more see what he looked like than she had been able to before. "That is the best I can do," he panted. "I'm afraid that the more slowly I move, the more spread out I become. That is the way things are here in quantum land. The smaller the space you occupy, the faster you have to move. It's one of the rules, and there is nothing I can do about it." There isn't really room to slow down here," continued Alice's companion as he began once more to leap rapidly around. "The platform is becoming so crowded that I have to be more compact." Sure enough, the space in which Alice stood had now become very crowded indeed, being closely packed with the small figures, each dancing feverishly to and fro. "What strange beings," thought Alice. "I do not think I shall ever be able to quite see what they look like if they will not stand still for a minute, and there does not seem to be much of a chance of that." Since it did not look as if she would get them to slow down, she tried another topic. "Would you please tell me what sort of platform we are on?" "Why, we're railway platform, of course," replied one of the electrons cheerfully. It was very hard for Alice to say which had spoken. They really did all look very much the same. "We're going to take the wave train to the screen, you see. You will change there to the Photon Express, I expect, if you do not want to go any further. If you want to go any further." "Do you mean the television screen?" asked Alice. "Why, of course I do," cried one of the electrons. Alice could have sworn that it was not the same one which had just spoken, but it was very difficult to be certain. "Come on, the train is here and we have to get on." Sure enough, Alice could see a line of small compartments drawn up on the platform. They were very small. Some were empty, some had one electron in, some had two. All the empty compartments were filling rapidly. In fact, there did not seem to be any left. But Alice noticed that not one of the compartments held more than 2 electrons. As they passed by one of the compartments, the 2 occupants would cry out, "No room, no room!" Surely you could squeeze more than 2 into a compartment, seeing as the train is so crowded, Alice asked her companion. "Oh, no, never more than 2 electrons together, that is the rule." "I suppose we shall have to get into different compartments then," declared Alice regretfully, but the electron reassured her. "There's no problem there for you, no problem at all. You can get into any compartment that you want to, of course." "I am sure I do not see why that should be," Alice replied. "If a compartment is too full to hold you, then it must be surely too full for me to fit in there as well." "Not at all. The compartments are only allowed to hold 2 electrons, so almost all the places for electrons may be taken up. But you are not an electron. There is not a single other Alice on the train, so there is plenty of room for an Alice in any of the compartments." This did not seem to follow so far as Alice could see, but she was afraid that the train would start to move off before they got seats. So she began looking for an empty space that could take another electron. How about this one, she asked her associate. Here is a compartment with only one other electron already in it. Can you get in here? Oh, certainly not, he snapped, sounding quite horrified. That is another spin-up electron. I cannot share a compartment with another spin-up electron. What a suggestion. It is quite against my principle. You mean against your principles? Alice asked. I mean what I say, against my principle, or rather, the Pauli exclusion principle. It forbids any two of us electrons from doing the same thing, which includes being in the same space and having the same spin, he responded crossly. Alice did not really know why she had upset him, but she looked around hastily to find another compartment which might suit him better. She managed to find another one that held a single electron who was of the spin down variety, and Alice's companion leaped into this one readily enough. Alice was surprised to find that although the tiny compartment now seemed full, there was somehow enough room for her to fit in there quite easily. Notice no sooner were they settled in than the train was off. The journey was uneventful and the scenery not very interesting, so Alice was rather glad when the train began to slow down. This must be the screen, I suppose, thought Alice. I wonder what will happen here. As they alighted at the screen, there was an enormous bustle everywhere. What is going on? Alice wondered aloud. Why does everyone seem to be so excited? Her questions were answered by an announcement which appeared to come from the air all around her. The screen phosphor is presently being excited by the incoming electrons, and we shall be having photon emission soon. Stand by for the departure of the Photon Express. Alice looked around to see if she could see the express arriving, when there was a rush of bright shining shapes across the platform. Alice was caught in the middle of the crowd and carried along with them as they all crowded into one compartment. Well, they do not seem to be worried by any principle, Pauli or otherwise, thought Alice as they crowded in around her. These ones are certainly not worried about being all in the same place. I suppose the express is going to start soon. I wonder where we shall end up, she concluded as she stepped onto the platform. My, that certainly was a fast journey. Why, it seemed to take no time at all. Alice was quite right about this. The journey did indeed take no time at all, as time is effectively frozen for anything which is traveling at the velocity of light. Once again, she found herself surrounded by a crowd of electrons, all rushing away from the platform. Come along, one of them cried to her as it rushed off. We must get out of the station now if we are to get anywhere. Excuse me, Alice said tentatively. Are you the same electron that I was talking to before? Yes, I am, answered the electron as it darted off down a side passage. Alice was swept along by the crowd of electrons and carried through the main gateway from the platform. I declare this is really too irksome, said Alice. Now I have lost the only person I know at all in this strange place and have no one to explain what is happening. Don't worry, Alice, said a voice about knee level. I will show you where to go. It was one of the electrons. How do you know my name? Asked Alice in surprise. Oh, that's simple. I'm the same electron that you spoke to before. You cannot be, explained Alice. I saw that electron go off in a different direction. Perhaps he is not the same one as I was talking to before. Certainly he was. Then you cannot be the same one, said Alice reasonably. You cannot both be the same one, you know. Oh, yes, we can, replied the electron. He is the same, I am the same, we are all the same. You know, exactly the same. That is ridiculous, argued Alice. You are here beside me. Well, he has run off somewhere over there, so you cannot both be the same person. One of you must be different. Not at all, cried the electron, jumping up and down even faster in excitement. We are all identical. There is no way whatsoever you can tell us apart. So you see that he might be the same and I am the same too. At that point, the crowd of electrons which surrounded Alice all began to cry out, I am the same too. I am just the same as you are. I am too, said the same as the other ones. The tumult was dreadful, and Alice closed her eyes and put her hands over her ears until the noise died down again. When it was quiet again, Alice opened her eyes and lowered her hands. She found that there was no sign of the crowd of electrons which had been clustering around her, and that she was walking out of the station entrance all alone. Looking around, she found herself in a street which at first sight seemed quite normal. She turned left and began to walk along the sidewalk. As she walked, she came along an empty plot by the side of the road, where a group of builders were clustered around a pile of bricks. Alice assumed that they were builders as they were unloading more bricks from a small cart. Well, at least these people seem to be behaving in a sensible manner, she thought to herself. Just then another group came around a corner carrying out what looked like a very large rolled up carpet and proceeded to spread it out on the site. When it was unrolled, Alice could see that it was some sort of building plan. It did seem to be rather a large plan since it covered most of the available space. Well, I do rather believe it must be exactly the same size as the building they are going to put up. But how will they manage to build anything if the plan is already taking up all the room? The builders had finished easing the plan into position and retreated to the pile of bricks. They all picked up bricks and began to throwing them at the plan, apparently quite at random. All was confusion. Some fell in one place, some in another. And Alice could see no purpose at all what they were doing. She asked the person who was standing to one side. "Well, what are you doing?" she asked the person who was standing to one side. He appeared to be doing nothing, and she assumed him to be the foreman. "You're just making an untidy pile of bricks. Aren't you supposed to be putting up a building?" "Ah, sure, and we are, me darling," answered the foreman. "It's true. So it is that the random fluctuations are still large enough to hide the pattern. But since we have laid down the probability distribution for the results we are after, we'll be getting there, never fear." Alice felt that this display of optimism was not very convincing, but she kept her peace and watched as the shower of bricks continued to descend onto the site. Gradually, to her amazement, she noted that more bricks were falling in some regions than in others, and she could begin to make out the patterns of walls and doorways. She watched in fascination as the recognizable shapes of rooms began to appear out of the initial chaos. "Why, that is amazing," she cried. "How do you manage to do that?" "Well now, haven't I told you?" smiled the foreman. "You watched us lay down the probability distribution before we began. This specifies where there should be bricks and where there should be none. We must do this before we start bricklaying, as we cannot tell where each brick will go when we throw it. You know," he continued. "I do not see why," Alice interrupted him. "I am used to seeing bricks being laid in place one after another in straight lines." "Well now, that is not the quantum way. Here we cannot control where each individual brick goes, only the probability that it will go one place or another. This means that when you only have a few bricks, they can go almost anywhere and seem to have no sort of pattern at all. As the numbers become larger, however, you find that there are bricks only where there is some probability that there should be there. And where the probability is higher, you get more bricks. When you have large numbers of bricks involved, it all works out very nicely in the end, so it does." Alice found this very peculiar, although the foreman spoke so definitely that it sounded as if it might make some sort of strange sense. She did not ask any more questions at this time, as his answers only made her feel more confused than ever. So she thanked him for his information and went on down the road. Alice walked along and saw a large bank, and when she stepped through the doorway, she found herself in a large pillared hall with marble walls. It looked very much like other banks that she had been to, but only more intense. There was a line of cashier windows along the wall, and the vast floor area was divided up by portable tape barriers, so that the customers would be guided into regular lines as they waited to be served. At the moment, however, the place appeared to be quite empty of any customers at all. Apart from the cashier behind the counter and a bank guard standing by the door, Alice did not see anyone. As she had been advised to ask for information at the bank, she began to walk purposely toward the distant line of windows. "Now, you just wait a minute," called the guard by the door. "Where do you think you're going, young miss? Can't you see that there is a line?" "I am so sorry," replied Alice, "but I actually can't see a line. There are no people here." "There certainly are, and a lot of them," answered the guard emphatically. "We seem to have quite a rush of no people today. Usually, though, we refer to them as virtual. I have seldom seen quite so many virtual particles waiting to get their energy loans." Alice had a by now familiar feeling that things were not going to become all that much clearer very quickly. She looked over at the window and saw that, although the room still appeared to be quite empty, The cashiers were all very busy. As she watched, she saw bright figures appear one at a time in front of one till or another, and then rush quickly back from the bank. At one till, she saw a pair of figures materialize together in front of a grill. One she recognized as an electron. The other one was very similar, but was a sort of photographic negative of the first, opposite in every way to the electrons she had seen previously. "That is a positron, an anti-electron," murmured a voice in her ear. Alice looked around and saw a severe-looking, smartly dressed young woman. "Who are you?" she asked. "I am the bank manager," replied her companion. "I am in charge of the distribution of energy loans to all the virtual particles here. Most of them are photons, as you can see, but sometimes we get pairs of particles and antiparticles who come along together to ask for a loan, like the electron and positron pair that you were just looking at." "Why do they need an energy loan?" asked Alice. "And why can't I see them before they get it?" "Well, you see," replied the manager, "in order for a particle to exist properly, so that it can be a free particle and able to move around and be observed normally and so on, it has to have, at the very least, a certain amount of minimum energy, which we call its rest mass energy. These poor virtual particles do not even have that energy. Most of them have no energy at all, so they do not really exist. Fortunately for them, they can get a loan of energy here at the bank, and this allows them to exist for a little while." So there's a line that says delta E, delta T equals the Heisenberg uncertainty principle. That is called the Heisenberg relationship. It governs all our transactions. The H is called Planck's constant, and a correctly reduced value, of course. The relation gives the rate of exchange for our energy loans. The quantity delta E is the amount of energy which is borrowed, and delta T is the period for which the loan is made. "You mean," said Alice, trying to follow what the manager was saying, "that it's like an exchange rate between different types of money, so that the more time there is, the more energy they can have." Oh no, quite the reverse. "It is the energy and time multiplied together which are constant. So the greater the amount of energy, the shorter amount of time they are allowed to keep it. If you want to see what I mean, just look at that exotic particle and antiparticle which have just taken out a loan at window number 7. Alice looked where she was directed and observed the striking sight. In front of the window was a pair of figures. One was the opposite of the other, in much the same way as for the electron and positron that she had seen earlier. This pair, however, were bright, flamboyant figures, taking up so much space of their presence that they quite obscured the cashier behind them. Alice could not but be impressed by the extravagance of the two. But as she opened her mouth to make a comment, they grew hazy and then vanished completely. "That is an illustration of what I was saying," continued the manager. "The pair took out an enormous energy loan to support the huge rest mass that they needed for their lifestyle. Because the loan was so large, the repayment time was very, very short indeed. So short that they did not even manage to leave the counter before it had to be repaid. Because such heavy particles cannot get very far before they have to repay the energy loan, they are known in the trade as short-range particles," she added. "Is this the relationship between time and energy the same for everyone, then?" asked Alice, who felt that she might have discovered something definite at last. "Oh, yes, indeed. The Planck's constant is always the same whenever and wherever it is applied. It is called a universal constant, which simply means that it is always the same everywhere. We deal with energy at the bank here," continued the manager, "because energy acts as the currency here in quantum land. As you would express your currency in dollars, the unit of energy that we use most of the time here is called the EV. How much energy a particle has determines what it is able to do, how fast it can go, and what state it can get into. How much it will be able to affect other systems, these all depends on the energy that it has. Not all particles are completely destitute like the ones that are lining up. Many of them do have sufficient energy of their own. And in that case, they can keep it as long as they would like. Those are the ones which you have been seeing moving around outside. Any particle which needs to have a mass has to have energy just for it to exist. She pointed out another framed notice on the wall which read, mass is energy, energy is mass. If a particle wants to have mass, then it must find the energy to support it somehow. If it has any energy left over, then it can use it to do other things. Not all particles bother with mass, she added. There are some free and easy bohemian particles. I love the word bohemian, I don't know why.
Bohemian Rhapsody?
You're a bohemian, don't know what it means. So there are some free and easy bohemian particles. That's a good word for Cohen. Cohen the bohemian. Particles which do not have any rest mass at all. They are not tied down like most particles who have to provide for their mass. So they can make use of even a small amounts of energy. Photons, there's your photons. Photons are a case in point. A photon has no rest mass, so a photon at rest would not weigh anything at all. Mind you, you do not normally find photons at rest. They are forever rushing about at the speed of light, as photons are what light is made of. Light is not a smooth, continuous stream. It is made up of a lot of quanta, little particles of energy, so that the flow of light is lumpy. That's a good word. That's a technical term. Lumpy. These quanta, or particles of light, are called photons. Practically everything comes in quanta of some size. This gives quantum physics its name. Look at all those photons leaving the bank now. Basically, photons are all the same, except exactly like one another in the way that electrons are all the same. But you may notice that many of these photons seem quite different. That is because they have different amounts of energy. Some of them have very little energy. Some of those, like radio frequencies, don't have very much energy at all because they have such a long wavelength. Alice looked down at a crowd of photons which was rushing past her, flowing around her feet and out through the door. As they went, she heard snatches of music, dramatic voices, and something about doing lunch on Thursday. I didn't know what radio waves were made of. I didn't know that radio waves were made of photons, admitted Alice. Oh, yes, indeed. They're very long wavelength photons, of course, with low frequency and very little energy. They're very gregarious because if they are to have any noticeable effect, you need a lot of them at once. Friendly little fellows, aren't they? Smiled Alice's companion. Visible photons now, the ones which make up the light that people are used to seeing, they have higher frequency and more energy. One of those can have quite a noticeable effect. The really affluent ones, the big spenders, are the X-rays and the gamma photons. Each one of those carries a lot of energy around with it, and they can really make their presence felt on their surroundings if they choose to interact. That is certainly very interesting, said Alice, not entirely and truthfully, but I still feel confused about the whole idea of energy. Can you tell me what energy actually is? Good question. Well now, replied the manager with satisfaction. That is a very sensible question to ask. Unfortunately, it is not very easy to answer. Come into my office and I will try to give you an explanation. Manager led Alice briskly across the tiled floor of the main hall through an unobtrusive but rather forbidding door in one corner. There was a large modern office. Motioning Alice to sit down in a deep, comfortable chair in front of the desk, the manager went around and sat in the chair behind him. Well, she began, energy is a little bit like money in your world, and it's not too easy to say exactly what it is either. I should think that was quite easy, responded Alice. Money is like coins, or in my pocket, or cash. It can be like banknotes. That is cash, which is certainly one form of energy, but one form of money. But money does not have to be in notes and coins. It can be in a savings account, for example, or in stocks and shares, or even invested in a building. In much the same way, energy can take different forms, which seems quite different from one another. Okay, so there's that. So if you want a weird graduation present, ask for Alice and quantum. Or the other one, there are no electrons. So, there are no electrons. That's that book with the, where like it's the greenies and they want to go party.
He talked
We
about
talked, no,
once.
we talked about that book. We did.
We did?
Yeah, we did. Okay, so, math.
You turned off the TV. Hey, I can't see that Birdman.
Why did you go?
Because then we're screwed on the assignment.
That's foul.
He's still gonna.
He's still gonna sign it.
It's like not my fault, you should have told me you couldn't see.
Kevin, that's not how this works. Yeah, okay, we got
Bohemian.
reserve lines.
Yeah, what was that? What was that?
That stalks back then.
Bohemian.
What really confused me is.
Okay.
All of us to cool our minds.
We got 3 lines. Okay. I understand. And one that is quantum number. Hey. Energy level.
Kinda.
So wait. Dang it.
Good enough.
Oh, that's actually gonna be 80.
I have not seen this since
That's
season
really,
2.
that's really stupid, actually.
That is terrible.
Yeah.
Okay. So this relates back to the story of Alice in Quantumland. So, and it also ties in with the photoelectric effect. So what they figured out, and a lot of times you see these energy diagrams drawn like steps like on a ladder. And sometimes you see them as negative values, sometimes you see them where they're going to start at 0, but it's all kind of playing out the same. So when you see these numbers, so they're going to say that electrons have a particular energy level. And you can equate that with a certain distance, okay? And say, okay, and this is the whole idea when you talk about electrons. And that was the kind of what I want you to get from that book, is that, you know, and this is the downfall of science and how we've screwed you guys over when we taught this. And we draw these nice little circles and go, oh, here's electrons moving around. In reality, we don't know what they're doing, okay? We don't. There's regions of probability. That's all I can say, right? Because again, because in the Heisenberg uncertainty principle is that when you try and find the electron, then you completely screw up where it might be. You find it, but then you don't know where it is after that. Energy levels, ironically, we know with a higher degree of precision. And here's why we know more about their energy levels than we knew about the position. And if you shift that paradigm from saying, oh, I want to know what the electrons are doing, don't, okay? You're not going to win. You cannot win. Okay, and everybody says, I want to see an electron. You can't. Get over it, okay? No, you can't. But what we do know is we know that the energy levels that they have. Now, the reason that we know so much more about their electrons and what their energies are is because when you look at, and you all have seen those, like bright line spectrums, like you would have a red line, and then you'd have a green line, and then you'd have like maybe a couple of purple lines. Y'all remember in Chem 1, y'all looked at bright line, you know what I'm talking about, okay? And this is what's known as an emission spectrum. So, and this is where science becomes a tapestry and where you had to have things develop at the same time. So, initially, they didn't even have the capacity to separate out the light. So that was a science in and of itself. Like, how do you get light separated into these bands, okay? And you use what's called a diffraction gradient. So that's one way, and it separates these lights out. Cool. And then, and this goes back to the classical idea of mechanics. If here's the nucleus, and these electrons could exist at any energy level, at any distance away, then when you look at the spectrum, if these electrons can make infinite numbers of jumps of energy, every element should produce the continuous spectrum of light. You would have Roy G. Biv, you would have every color. There would be no difference in the spectrums. If the electrons could exist at any energy level, every spectrum from every element would look the exact same. But that's not what happens. You get each element with unique spectrum. So it's like a fingerprint. Well, the only way that you can have these distinct bands of light is if they exist with distinct amounts of energy. So, because of the fact that these aren't blurry lines, these are bright line spectrums. These are very, very distinct bands of light. And the only way you can have very, very distinct bands of light is if they have very distinct amounts of energy. So the uncertainty comes in the position and the momentum. The uncertainty doesn't come from the energy, okay? Because if the uncertainty came from the energy side of it, then the lines would be fuzzy, okay? There's some uncertainty in the energy, so we're going to get fuzzy lines when we look at the spectrum. We don't get fuzzy lines. We get very, very clear lines. And again, the only way you can have clear lines is if you have very clear, distinct amounts of energy. So, okay, well, great. How do we determine how much energy is in them? How do you find out, oh, here's, like, this is white light being emitted, which is the entire spectrum. How do I differentiate and pull out just the red light versus the green light versus the purple light? And then, better yet, how do I find the energy in one, count it, one photon that's traveling in that wave? And that became the incredibly difficult part of this. How do you determine the actual amount of value? And that's where Planck's constant comes in. So if you remember the energy of this, you can write it as h nu, you can write it as hc over lambda. But here's the whole point of this. So if you look at one of the key things that they did, they said, ooh, now we know how much energy had to be involved in producing that red light. How much energy was involved in the purple light. So the only way that you can generate these distinct bands of light is if the electrons existed in distinct energy levels. And then you could, once you figured out what that light was, then you can go, oh, that's how much energy that there is. So then you work backwards and go, okay, well, there is a red light. There's one distinct band of red light. Cool. That means that if you can find the energy of that red light, that had to represent